back to page 1 here and move into the information. I do have some good news before we start. The superposition in AC is actually easier to think of, but more involved because of the phasors, but it's easier to accomplish your goals in the AC world, which sounds really strange. So let's go over the definition at the top. Was introduced, superposition, introduced in Chapter 8 for DC circuit analysis. And what it says here in the middle, right here, the current in any given branch of a multiple source circuit can be found by determining the currents in that branch produced by each source, each power supply, each current source acting alone, with all the other sources replaced by their internal impedances. Remember, a power supply has an internal resistance of theoretically 0, while a current source has an infinite amount of impedance. We use a short to simulate the power supply. We use an open to simulate a current source. So the current is found in each branch produced by each source acting alone, with other sources replaced by internal impedances. The total current, this is the important part, the total current in a given branch, and that branch could have one resistor or two or more, is the phasor sum of the individual source currents in that branch. Interesting. It was a little different in the DC world. We had to draw arrows and come up with schemes to figure out which currents we're adding, which currents we're subtracting. What you've just heard means that the currents in a particular circuit is what we're going to be solving for. And once we get the currents, it's just Ohm's law away from getting the voltage. But more important, when we find the individual currents contributed to by each source, they simply add and subtract naturally through the process of addition, because their phase angles will perform the subtraction for us. So there are 4 steps. Number 1, leave one of the sources in the circuit. I'm right here looking at this. Leave one of the sources in the circuit, replace all others with their internal impedance. For ideal voltage sources, the impedance is 0. For ideal current sources, the internal impedance is infinite. We will call this procedure zeroing the source. Interesting term. Number 2, find the current in the branch of interest produced by the only power supply in the circuit, and then do this step over and over for each power supply. And then step 4 just says, just add these things together, and you're done at that point. Okay? All right, so here we go. Page 3. We're actually going to work a circuit at this point. This is just a simple T circuit with 2 power supplies. We want to find the current through the first resistor. So our goal will be to find the current through this resistor that I can't seem to draw yet, through this resistor IR1. That happens to be the total current when the first power supply on the left is discussed. So there's no need to draw any arrows. There's no need to worry about anything. Let's just work 3 problems and get good at this. All right, so the first circuit is shown there in the picture. And you notice I shorted the supply on the right. It's a voltage source, so it got shorted. And I'm asking you, what is this circuit in the red? What What is that? If you said that it was parallel, you are correct. If you said it was parallel, you are correct. Okay? Now, we want to grab that parallel branch over here and collapse it down to 2.121 at 45. We know the 45 is good because 3K and 3K of inductance and resistance would produce that in parallel. And the value is actually somewhere less than 3K. So we've got a good value there. And we collapse the circuit. Now the circuit collapses to this value right here, to this circuit. And you notice how quickly we get to a series circuit. Now what we're after is this current, which is part of this series circuit. So the best way to find total current is to get the total impedance check done. And I recommend you try these and don't forget to put brackets around everything or the answers will come up with errors. And our ZT is 2915.17 at 30.962 ohms. So here's what we're after. The total current, which is shown here. And we can say that the total current is the current in R1 from source 1. That's what the S1 means, source 1. So if you want to label this source 1 and source 2, our next goal is to find. We went out and calculated the current twice through the yellow resistor, okay? And the other side of the current coming from this supply right here. So again, we want this current here, and that may require a slightly different approach. So let's go and solve it. And we notice that this particular branch is in parallel. And we hit it. Now, notice my creative labeling. This is called impedance of R1C1. This keeps you from going insane so that you always know what you've combined. There are only two components, so I go product over sum, and I come up with 948 some odd ohms. I didn't put the units in there. You might want to add that in as part of your calculation. And as soon as you crunch that down, you're back to a series circuit. Now, you notice that you don't have the current going through there yet. You would need IT for that. And there are multiple ways to solve this problem. One way is to just go out there and get the voltage. So if I come out here and I find this voltage, then it's parallel, right? So if I find the voltage of that parallel, then I can Ohm's law my way into this current. So that's exactly what I did. I took the voltage of the current dividing situation and included the calculated value here on the top divided by the total, including resistor 2 here. And I came up with a voltage. That says that both of these components up here, see that much voltage. So independently of each other, they provide an Ohm's law current. So what I've got is, actually, I think I might have put a little typo in there. This is from S2, not from S1, because this is known as source 2. So you might want to put a little fix in there while I fix my notes here on my desk. There we go. And that allows us to calculate the current in R1. We're done. We're done. This is from source 2, and we add that source to the answer that we got on the last page, which is here. And of course, I have inverted them for some reason. So you're going to have to fix your notes here as you draw up your notes. This is actually source 2, and this is actually source 1. So make that bracket S1 and make this bracket S2 so that you've got your documentation correct. Now, what can we learn from this? We went out and we calculated the current. What we ended up doing was simply adding. You will add every time when you do AC circuits. You will not be subtracting at any point in time. And you see the minus 30 and the 14, they self-subtract to produce our final answer. Notice how I label it. IR1 total is the sum of IR1 from source 2 plus IR1 from source 1. Let's try another problem. This problem's a little different. This problem has a current source in it, which will present new interesting things that happen. And the circuit says, find IR3, which is right here. Find this current because of a current source and because of a power supply. So this is known as IS1. This is known as VS1, source 1. And we're going to attack this by taking the current source out on one side. And quickly what you notice is you have an open here. And that means that this resistor that you're trying to find the current through is hanging in the wind, which means there's no current from the supply on the left is unable to get any current through that resistor. That's because of the impedance of this current source is very, very big. So the contribution to part 1 of the circuit is 0. Isn't that interesting? Okay, now part 2 is even more interesting because we have a current source, IS1, that's dropping 5 milliamps into that resistor. No way, no way. Can't be that easy, right? There is no extra work required. IS1 flows into R3, 5 milliamps, all 5. Final answer, the first supply plus the second supply, 5 milliamps. Wow, ain't that special? And that problem, you know, is like myth. That doesn't happen. That does not happen all the time. All right, next problem. This is a humdinger. This is a big circuit. This is very similar to homework. You should go look at your homework questions so that you have something to guide you with, okay? So here we are. We have a current source on the left labeled IS1. We have a power supply on the right labeled VS1. And it's always good to know where the supplies are. Step 1, take this supply that's located to the right and short it, which we did. Okay, there it is in the picture. You're all happy to see it. And we've done step 1. Step 2, we want to find the current through IR1, which is right here in the middle of the circuit. So we take this branch, and it's in series, and simply add 1K at 90 plus 5K at 0 to get our total. And that drops in here, like that. Okay, sorry for the circuit shift. I'm trying to fix the circuit shift so that this does not happen. There we go. Okay. Let's see. I think we got it locked. Okay. So what we've got now is a need to get rid of some of these highlights that are out here. What we've got now is a circuit here that is in parallel. Well, here's how I look at it. Doggone it, if I could find the voltage, boy, if I could find the voltage, boy, doggone it, I have a current source. And a current source is feeding 1, 2, 3 parallel branches. Well, that allows me to solve in one step using current divider. So the biggest challenge is going to go out here and calculate ZT using the 1 over formula because you have more than 2 impedances. So we go out, we compute 1 over ZT to be 1381.39 at minus 16 degrees here, and we set up a quick current divider. The total current given, the branch that we want to know what is the total impedance of is the 1381 that we just calculated up above here. And down below is the impedance of the resistor that we care about, which is right here in the multiple circles of green, okay? That's a 2K at 0 degrees. And when we calculate it, we have figured out part 1 of the circuit. Isn't that interesting? Okay. Welcome back, ELE 112. This is chapter 20, Superposition Theorem. This is part 1 of several. I'm going to have a video for Thevenin's and a video for maximum power transfer theorem. So we're going to be studying the superposition theorem. That is a circuit with 2 or more power supplies, okay? The more power supplies there are, the more circuit analysis you get to do. If you take a look at the circuit on the screen, the last page computes from the other side. The current source is, you got it, the current source is opened, which means it doesn't exist. So I'm trying to find the current in IR1, right? Well, that resistor is in series. I've redrawn the circuit here. This circuit that's circled right here in, let's use a different color here. I took this circuit in red, was out here. It was out here, connected across the power supply and the resistor over here, actually. So I just moved the circuit to change perspective. And what I notice is that the battery is in series. The battery is in series with the power supply. Yeah, I can approach this in multiple ways. First thing I need to do is compute the combination here, because that combination will then lead me to a parallel circuit here. Now, what I'd like to do is find IT right here, because IT is what I'm after. IT, which is equal to IR1 from source, we'll call this VS1, okay, from VS1. And so we compress. We compress this parallel chamber here to get this value, leaving us a series circuit, which is then compressed. and therefore we are allowed to do IT, which is IR1 from the first source, is VT over ZT, and there's our answer. Now, that's not the final answer. The final answer is I have to take part 1 and part 2 from the current source and from the battery and add them together here to get 79.788 milliamps at minus 9.096 degrees.